So the third exam is going to be on Wednesday, July 7th. And that's covering sections 5.1 to 5.6. So we should get through all the material for chapter 5 this week. No class, remember, no class on Monday, July 5th, in observance of the 4th of July. So, time is tight. We've been missing quite a bit of class time here, but, that's the way it's set up. So last time we left off with number 155 in section 5.3. So now we are up to number 156, section still in 5.3. So number 156. All right. Find the area of a region D which is bounded by so this is the circle of radius 2, the line x equals root 3, the line x equals 2, and y equals 0. So what it is describing is the following. So we've got the circle of radius 2 in the first quadrant here. So this is y equals square root 4 minus x squared. And, and this is the line x equals 2 is right here, of course. The line x equals root 3 would be, say, right here. So here's the 1, and here's root 3. So we're looking at this region here. So we want to find the area of that. There's different ways to do this problem. So how can we describe this region? Okay, remember, right, we had, this general description of polar type regions. So there's simple polar rectangles, but then there's also like these kinds of things. So like here's angle theta 1, here's angle theta 2, and here is one function, r equals f of theta, and then another function here, r equals g of theta. And if you are this region here, then this is described as theta 1 is less than or equal to, maybe I shouldn't call it theta, let's say alpha and beta. Alpha less than or equal to theta, less than or equal to beta, and then the r is caught between the f and the g. So f of theta is less than or equal to r is less than or equal to g of theta. Okay, well, we've got, in this case, two curves here. We've got the circle, r equals 2. So the circle is r equals 2. And they gave it to you, of course, in rectangular coordinates. right? But you know that it's just r equal to 2 in polar coordinates. So what about this vertical line? How can you describe that vertical line? X equals root 3. So let's convert x equals root 3 to polar. Well, x is equal to r cosine theta. Equals root 3. Now I can divide by cosine theta, which of course is secant theta, like that. Right? So the region given here oh, and then of course we need the the range for the theta. So this is the point x equal to square root 3. X equal to square root 3, and then y is going to be equal to, I guess, what? Well, x is equal to this point here. So this is along the circle r equals 2. So along the circle of radius 1, the corresponding point is has got coordinates root 3 over 2 and 1/2. So this one's got coordinates root 3 and 1. All right, so here's root 3 and 1 for this coordinate here. And of course, halfway down at the circle of radius 1, this is the coordinate root 3 over 2, 1/2. So what is the angle here? If this is the point root 3 over 2, 1/2. What's the angle here? This is cosine and sine. So this angle here is what? If this is cosine and sine, this angle here is pi over 6. So the region being described here is 0 less than or equal to theta less than or equal to pi over 6. And then the r, right, the r is stuck between the line and the circle. So the upper bound for r is the 2. And the lower bound for r is this thing, root 3 secant theta. So this is the region given. Now, if you want to find the area of the region given as a double integral, using a double integral, the area is equal to the double integral over d of 1 dA. Right, double integral over d of just 1. So this is the double integral, describing this in polar terms, root 3 secant theta to 2, and then 0 to pi over 6, 1, and then the dA becomes r dr d theta. Okay, so because the region has constant bounds for theta, and then bounds for r in terms of functions of theta, we have to do r, you have to do dr d theta, rather than d theta dr. With just, ordinary polar rectangles where the bounds on the theta are constant and the bounds on the r are constant as well, you can do them in either order. You can do dr d theta or d theta dr. But for this type of region, it's got to be dr d theta. All right, so what do we get here? Antiderivative of r is 1/2 r squared from r equals root 3 secant theta to 2 d theta. right? So this is equal to the integral from 0 to pi, not pi over 2, pi over 6. Pi over 6, so 4 over 2 is 2, minus 3 halves secant squared theta d theta. Okay? And then the antiderivative in terms of theta so this is 2 theta, and then what's the antiderivative of secant squared? What's the antiderivative of secant squared is tangent, and that's from theta equals 2 theta equals pi over 6. So this is equal to 2 pi over 6 minus 0 minus 3 halves tangent of pi over 6 minus tangent of 0, evaluating each term one at a time. So this becomes pi over 3, and this becomes tangent 0. Tangent pi over 6, sine over cosine, so that's 1 over root 3, right? Because sine is a half, cosine is root 3 over 2. So you can just write 1 over root 3. Minus tangent of 0 is of course 0. So we get pi over 3 minus root 3 over 2. That's the final answer for the area of that region. There are other ways to figure the area of that region, I think. Maybe that's the best way to do it. All right. 166 Find the volume of the solid that lies under the double cone z squared equals 4x squared plus y squared, and inside the cylinder x squared plus y squared equals x, and above the plane z equal to 0. So we have the cone well, this is more of a tall, thin cone. So that's z squared equals 4x squared plus y squared. And then we've got the circle, x squared plus y squared equals 4x. So this is x squared minus 4x plus y squared is 0. So this is x squared minus 4x plus 4 plus y squared is 4. So this is x minus 2 squared plus y squared is equal to 4. So this is the circle whose center is at 2 on the x-axis and whose radius is 2. So the cylinder, maybe I should do it in red, is here. So what does the intersection of this cylinder and cone happen to be? Well, see if I can draw this a little better. Maybe I didn't quite draw that high enough, but the intersection of the cylinder and this is kind of this shape here. Okay, so we want the area under the cone, or sorry, the volume under the cone and above this circle. So volume under the cone and above, oh, this is not 1, this is 2, and then this is 4, and above the circle. Okay, so the circle, we'll call it D. So here's the circle D. Center is at 2, so it goes out to 4 and has 0, and it's got the equation x squared plus y squared equals 4x. So then in polar, this is r squared. X squared plus y squared is equal to r squared for r cosine of theta. So you can cancel the r's. So r is equal to 4 cosine theta. So now if you're going to rotate, if you're going to go through like some angles for theta equal to 0, you're here. For theta equal to 10 degrees, you're here. 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60, 70, 80, 90. So 90 degrees is right here, right? R is 4 cosine theta, and you go out to here. And now when you go out this way for R, or for theta, the r's are negative because cosine of theta from pi over 2 to pi is negative, so you pop out over here. Right, so this region D is equal to 0 less than or equal to theta less than or equal to pi, and then 0 less than or equal to r less than or equal to 4 cosine theta. If you want to equal 4 cosine theta, it takes you all the way out to the boundary of the circle. But if you want all the points on the inside, you just have less than or equal to. So this is the region D. So now the volume under the surface and above this circle, under the cone and above that circle, it's the double integral over D of, so what's this function here? This is z is equal to 2 square root x squared plus y squared. dA. Right, so it's the double integral of that function that is the cone, which is z equal to, so z squared is 4x squared plus y squared, so z is 2 square root x squared plus y squared. So now we transform this into polar coordinates. So double integral from 0 to 4 cosine theta, and then from 0 to pi for theta. X squared plus y squared is r squared. So this is 2r, like that. 2r. Unfortunately, the r's are going to be... Yeah, the r's are going to be negative as you go from 0 to pi. So what we're going to do is the following. So you have to take the positive square root. This is a positive quantity, square root x squared plus y squared. So let's just do the integral over. So since z equal to 2x squared plus y squared is symmetric around the x-axis, right? It's this cone. That function is this cone here. And if you flip the cone around if you reflect the cone around the xy plane, or not xy plane, the xz plane, I mean, it stays invariant, right? It doesn't matter if the x and y are positive or negative. The value of the function stays the same. So because of that, or what we could do is the following. Yeah, I see. What's a better way to do it? Instead of going from 0 to pi, what we can do is go from minus pi over 2 to pi over 2. I think that's better than this example here, or this approach, although this approach would work too. Right, so at negative pi over 2, the r is 0, and then at, 10 degrees, so that's minus 90, so minus 80, minus 70, minus 60, 50, 40, minus 10, and then 0, 1, 2, 3. So in that sense, the r's are always positive between minus pi over 2 and pi over 2. Still a span of 180 degrees. Okay, so this is the double integral from 0 to 4 cosine theta minus pi over 2 to pi over 2. Right, now if we're going to transform the polar coordinates, this is 2 square root r squared, r dr d theta. The square root of r squared is not r, it's the absolute value of r. But r is going to be bigger than or equal to 0 within this range here. Bigger than or equal to 0. So because r is bigger than or equal to 0, for minus pi over 2 is less than or equal to pi, theta is less than or equal to pi over 2, okay, absolute value of r is just r itself. So this becomes 0 to 4 cosine theta, so that's going to be 2r squared dr d theta. So this is equal to, antiderivative is 2/3 r to the third from r equals 0 to r equals 4 cosine theta, and then we'll do the integral d theta. So cubed, so 4 to the third is 64. 64 times 64 times 2 is 128. So 128 over 3 cosine the third theta minus at 0 is just 2/3. Oh, this is the wrong. Yeah, look at this here. Find the volume of the solid that lies under the double cone and inside the cylinder. X squared plus y squared equals x. I'm looking down here. It's x squared plus y squared equals 4x. It's supposed to be this one. X squared plus y squared equals x. I thought there was something that was wrong here. Anyway, we can just fix this. It's x squared plus y squared is equal to x. There's no 4 here. So it's just r equals cosine theta. And here, it's just x. So doing the same kind of trickery. This is x squared minus x plus y squared is 0. So I got x squared minus x plus 1/4 plus y squared equals 1/4. So this is x minus 1/2 quantity squared plus y squared equals 1/4. So this is the circle centered at 1/2 of radius 1, which is fine. It's the same kind of setup. And radius 1. So now the description is just like that. All right, so instead of 4 cosine theta, it's just cosine theta. So this is just 2/3 cosine to the third theta, and then r is equal to 0, so it's just 0. Okay, d theta, so this is the integral from minus pi over 2 to pi over 2, 2/3 cosine to the third theta. D theta. So, well, antiderivative of cosine to the third, how would you find that one? Does anyone remember how that one goes? Let's just go through Wolfram alpha to get a quick answer for that. So antiderivative cosine to the third x so it's 1/12 9 sine x plus sine 3. So this is 2/3 times 1/12 sine x. Okay. 9 sine x plus sine 3x. Sine 3x. All from minus pi over 2 to pi over 2. How do you do the antiderivative of cosine to the third? Does anyone remember? What you do is you write it as cosine theta, or not x, it's going to be theta in this case. You write this as cosine theta times cosine squared theta. So this is then cosine theta times 1 minus sine squared theta. And then you let u equal sine theta, and it cancels out the cosine theta. So why don't we do it that way rather than looking it up here on Wolfram alpha. All right, so this is equal to 2/3 integral from minus pi over 2 to pi over 2. So this is cosine theta times cosine squared theta d theta. So this is equal to 2/3 cosine theta 1 minus sine squared theta d theta. So then you let u be sine of theta, so du is cosine of theta d theta. So here's your cosine theta d theta. That just goes away. And so this is the integral from where to where. We'll let u be sine theta. So at minus pi over 2, this is u equals minus 1 to u equals 1, right? Because u is sine of theta. 1 minus u squared du. Well, so the antiderivative here is u minus 1/3 u to the third from u equals minus 1 to u equals 1. So you have 1 minus a third minus, and then at negative 1, it's like that. Oh, I lost my 2/3 here. So this is 2/3. So 1 minus 1/3 is 2/3, and then this is minus 2/3, so adding it. So it's 2/3 times 4/3, which is 8 over 9. Okay. So that's a nice problem. It was kind of involved, but I think that's a really nice display of how the integral using polar coordinates happens. Okay. I don't think you can do this with rectangular coordinates. Not too easily. Alrighty. So now we're into section 5.4. So we're up to first problem is 182. And 5.4. So we've made our way to triple integrals. All right. In this exercise, evaluate the triple integral over the rectangular box shown. So this is a triple integral over b, xy plus yz plus xz. dv, where b is equal to, well, what is it? 0 to 1 for x, 1 to 2 for x, 0 to 2 for y, and 1 to 3 for z. So it's truly a box in which the boundaries for x, y, and z are all just constants. Okay, so to calculate the triple integral, we set up a triple integrated integral in any order that we like because it's a box. You can do this in any order. This iterated integral in any order that you want. So we'll say 1 to 3 for z, 0 to 2 for y, 1 to 2 for x, x, y, y, z. Why is my value low? That's not what I mean. xy plus yz plus xz. So this is dz, dy, dx. Okay, we could have done it in any other order. And this is just a polynomial in x, y, and z. What does the triple integral calculate, by the way? Right, the double integral, geometrically it calculates a volume, right? So geometrically you can describe the double integral as a volume, but you can also, if you think of the function as a density function, and you integrate over a two-dimensional domain D, and you have this density function fxy over a two-dimensional domain D, then you can think of the double integral as a mass. So you have a density, and you integrate density over area, and you get mass. Integrate a variable density over area to get mass. So this way of looking at the double integral is one dimension less. So thinking of it as volume makes it a three-dimensional thing. Thinking of it this way makes it a two-dimensional thing. So once you get to triple integral, I mean, you got this box, right? So you've got this three-dimensional region, and you're going to be, integrating over this region. What does it represent? Well, you can't say it represents some four-dimensional volume unless you're, really kind of into that. What it is you've got this density function right here. So this is a density function for every point in that box. And now the triple integral is the integral of the density function over volume, which gives you the mass. Right? So that really is the sort of operative way of thinking about what a triple integral is. It no longer has just a geometric interpretation. You've got to add a little bit of physics to it. Okay, so let's do that. Mass calculation. This triple integral, or this mass calculation. So antiderivative with regard to z. So this is xyz plus 1/2 yz squared plus 1/2 xz squared from z equals 1 to z equals 3 dy dx. So this is equal to, so at z equals 3, this is 3xy plus 9/2 y plus 9/2 x minus yz, or not yz, sorry, xy. And here, plus 1/2 y plus 1/2 z. dy dx. So collecting like terms here, we get double integral from 1 to 2, and then 0 to 2. So we have 3xy minus xy, that's 2xy. Plus 9/2 y plus 1/2 y, so that's plus 5y. Same thing, plus 5x minus, or no, we already got that, minus xy there. dy dx. So antiderivative with regard to y, so that's xy squared plus 5/2 y squared plus 5/2 xy. Yeah, 3 terms. From y equals 0 to y equals 2 dx. So this is the integral from 1 to 2. So at 2, for y, this is 4x plus 4 times 5/2 is 10. Plus 5/2 xy, that's just 0. Minus, evaluating the whole thing as 0 gives me 0. So 4x. Dx, so that's the integral from 1 to 2. 4x plus 10 dx. Antiderivative, 2x squared plus 10x from 1 to 2. So this is 8 plus 20 minus 2 plus 10. So this is 28 minus 12. 28 minus 12 is 16. Let's double check this. So 1/2 xz squared, 1/2 yz squared, xyz from 3 to 1. So it's 2xy plus 9/2 y minus 1/2 y. Minus. Right, evaluating at 1, this is xy minus 1/2 z squared. Right, so instead of 5s here, there's 4s. And then 4/2. And then that one's still 4. 4xy. So at 2, this is 4x plus 8 plus 0 minus 0. These are all 0. So it's 4x plus 8. So at 2, you're going to get 8 plus 16 minus at 1, you're going to get 10. So 26 minus 10 is 16 again. Why did I?
Would it not be, we have 4x plus 8 plus 0? Shouldn't that 0 be 8x? Because the 4xy, when you plug 2 into y, you would get 8x.
So you plug in 2 here. 4x. Oh, yeah, 8x. Yeah. Right. I was putting the 0 there. It's y equal to 2. Yeah, so 8x. So 4x plus 8x, that gives you 12x. So it's 6x squared plus 8x. So at 2, it's 24 plus 16. Is 40 minus 10 is 30. Still not what I expected. What is going on here? Do we have this correct? 1 to 2, 0 to 2, 1 to 3. 1 to 2, 0 to 2, 1 to 3. And this is dz, dy, dx. dz, dy, dx. So x, y, z plus 1 half y, z squared plus 1 half x, z squared. So at 3xy plus 9 halves y plus 9 halves x minus at 1 xy minus 1 half minus 1 half x. This is an x. So 9 halves minus a half is 8 halves, is 4y and 4x. And then 3 minus 1 is 2. So this is xy squared with regard to y, 2y squared plus 4xy. So at y equal to 2, this is 4x plus 8 plus 8x. That's 12x plus 8. So that is 6x squared plus 8x at 2. It's 24 plus 16. No, this is correct. So we got 30. Okay. So that was number 182. Next problem is 186. In the following exercises, change the order of integration by first integrating with respect to z, then x, then y. So this is dx, dy, dz. Now there's 6 ways to order that. Right? There's 3 factorial, 3 times 2 times 1. So, x, y, z, x, z, y, y, x, z, y, z, x, and the last two, z, x, y, and z, y, x. So with a box, that can be done in any of the 6 orders when all of the boundaries are constants. So this is 0, 1, minus 1, 1, 0, 3. Z, E, X, Z, e to the x plus 2y. And this is dx, dy, dz. All right, so then do it dz, dx, dy. So because the bounds are constant, all bounds are constant, we can reorder the integral in any of the 3 factorial equal to 6 ways possible. So they're saying do dz, dx, dy. So z e to the x plus 2y dz, dx, dy. Is that what they said? Zxy, right. So the z is 0 to 1. Right, the z is 0 to 1. The x is 0 to 3. Right, the x is the inner integral, so that's 0 to 3. And then y is the last remaining one, minus 1 to 1. Right, these are the boundaries for x, y, and z. Right, 0 to 3 for x, minus 1 to 1 for y, 0 to 1 for z. So this is zxy from right to left. All right, so 0, 1, 0, 3, negative 1, 1. You can do that in any order that you like for a box, for an actual square box. So We'll do the antiderivative with regard to z. 1/2 z squared e to the x plus 2yz from z equals 0 to z equals 1. So just evaluating at z equal to 1, and at 0 it's 0. So this is the integral from -1 to 1, 0 to 3, 1/2 e to the x plus 2y dx dy. So antiderivative with regard to x, 1/2 e to the x plus y x 2xy from x equals 0 to x equals 3 dy. So at 3, 1/2 e to the third plus at x equal to 3 is 6y minus at x equal to 0 is 0. Right? At x equal to 0, this is, or no, sorry. At x equal to 3, we get e to the third, and then at x equal to 0, you get 1 here, or 1/2. 1/2 plus 0. Or minus 1/2, because we're subtracting. So now, antiderivative with regard to y. This and this are constants, right? So it's 1/2 e to the third minus 1 times y plus 3y squared from -1 to 1. Right, so this one cancels out and goes to 0 because it's the same value at 1 and -1. But this one gets doubled. So it's just e to the third minus 1. Okay. Now, you can calculate it in any of the 6 ways, and it would give you the same answer. But, I'm not going to do this one here. We want to get to a few more interesting problems to actually do that kind of thing. Like double check the integral. Usually the constant values are pretty boring. So that was 186, 188. I think it's the same thing, isn't it? Yeah. Is there anything going on with 188 that makes one ordering better than the other? There's nothing. There's nothing going on there. Well, let's give it a shot. So 1 to 2, minus 2 to minus 1. Zero to 1, x plus y over z, and then this is dx dy dz. So again, these numbers mean 0 is less than or equal to x, less than or equal to 1. Right? -2 is less than or equal to y, is less than or equal to -1. And then z is 1 is less than or equal to z, less than or equal to 2. So these are bounds for x, y, and z. Which one is which, is given by the dx, dy, and dz. So rewrite in terms of same thing, right? Y, x, and then z. dz, dx, dy. dz, dx, dy. So this is x plus y over z, dz, dx, dy. So z goes from 1 to 2. X goes from 0 to 1. Y, oops, that's a y. y goes from -2 to -1. So what is the antiderivative with regard to z here? So x and y are constants. We're just doing the antiderivative with regard to z. What is it? So this is, this function is x plus y, which is a constant, times 1 over z. So the antiderivative is what? Antiderivative with regard to z. Right? Just x plus y times the natural log of z. So this is 0 to 1, -2 to -1, x plus y times the natural log of z, from z equals 1 to z equals 2. So this is d, and what's left is dx dy. So this is natural log of 2 minus natural log of 1. Dx dy. Natural log of 1 is 0, so we just have natural log of 2 times that. So I'm gonna bring the natural log of 2 out front. So now it's the integral from -2 to -1, integral from 0 to 1, x plus y dx dy. Antiderivative with regard to x. So this is 1/2 x squared plus xy from x equals, oops, I already did the, so that goes away, from x equals 0 to x equals 1. And then we're left with dy. So natural log of 2, integral from -1 to 1. So at 1, you just get 1/2 plus y. And then at 0, you get 0. So antiderivative of 1/2 plus y is 1/2 x plus, 1/2 y plus 1/2 y squared, all from y equals -1 to 1. So natural log of 2.
Where did the -1 and +1 come from?
Oh, -2 to -1. Y equals -2 to y equals -1. So this is at -1, so it's -1/2 plus 1/2 at y equal to -1. Right? -1/2 plus 1/2. And then at -2, this is equal to, what we got here? -2 times 1/2 is -1. And then this stays positive. 4 over 2 is 2. So -1 plus 2 is just -1. And of course, that's 0. So it's just 1, -1. So the answer is negative natural log of 2. I think that problem is only interesting in how the antiderivatives worked. Because you have that z on the bottom there, you actually got to bring in the natural log antiderivative. Okay. So 7:32. Let's take 5 minutes. Okay, everybody, we are back. So we are on to number, so that was 180, that was 188, so we're on number 192 now. So number 192, let's just leave that one out. Let's just leave that one out. So 192, we'll omit that one. 198 looks more interesting. So evaluate the triple integral x dv. So evaluate the triple integral x dv over E, where E is, and here they just give you the description of that region. So minus 2 is less than x is less than 2. So minus 2 is less than or equal to x is less than or equal to 2. Y is caught between minus 4 is times square root 1 minus x squared is less than y is less than the square root 4 minus x squared. And then z is between 0 and 4 minus x squared minus y squared. Okay, so this is E. Okay, so I'm going to write this in terms. So since you've got the region that described in this way, okay, we have. So with three-dimensional regions, we don't have like type 1, type 2 anymore. There's like type 1, 2, 3, 4, 5, and 6, but who could keep track of which is which, right? So, it's just in whatever order you presented it. So here you have x bounded by constants, y bounded by functions of x, z bounded by functions of x and y. So you go, one variable each time on the boundaries. So constants, one variable before, and then two variables before. All right, bounded by functions of two variables or before. So you have to do this in terms of dz, dy, dx, right, from bottom to top, unless you can rewrite this interval in another way, which I don't think you can here. So, but anyway, this one will have a pretty reasonable way of going about it. So this is 4 minus x squared plus y squared. I'll write it like that. Well, no, we'll just do 4 minus x squared minus y squared. And then minus 4, 1 minus x squared, 4, 1 minus x squared, and then minus 2 to 2. Hold on a second. Oh, right. Yeah, that's the circles of radius. Radius. Something's not right here. X goes from minus 2 to 2. These 4s are supposed to be on the end. Oh, yeah, look. See? That's a typo right there. So, typo. Let me note that. Oh, I already have it noted. Look at that. That's a typo right there. See it? This 4 right here is supposed to be there. It's supposed to be square root 4 minus x squared. Minus the square root 4 minus x squared. And here they have square root 4 minus x squared, positive square root 4 minus x squared. So that 4 and the 1, this 1 is supposed to be the 4. So, boom, boom. So that's 4, 4, 4, 4. All right, and we have x, and then this is dz, dy, dx, and again going from bottom to top. Okay, so first antiderivative with regard to z. Well, x is a constant, right? So square root 4 minus x squared, the negative, square root 4 minus x squared, the positive, x times z, from z equals 0 to z equals 4 minus x squared minus y squared. That was 4. Yes, that's correct. And starting at 0, starting at 0. And then dy dx. So this is just 4 minus x squared minus y squared times x here. Oops. So integral from from minus 2 to 2. So this is x times 4 minus x squared minus y squared, dy dx. Now, okay, let's take a look at this double integral. Now, we could now do the antiderivative with regard to y, but what problem would we pop up with if we did? I can do the antiderivative. I mean, so there's 4x minus x to the third minus xy squared. If I did the antiderivative with regard to y, then what would I have to deal with? You know, then I'd be left with a bunch of terms like of the form x squared, like 4 minus x squared to the 3/2 power, or something like that, you know. Those would require trigonometric substitutions, which, you know, we don't want to go that way. You know, but what region is being described here? Right? What domain is being described here? Do you see it? Right? 4 minus x squared minus square root 4 minus x squared is the top half of the circle of radius 2. And the negative one, of course, is the bottom half of the circle of radius 2. And the x coordinate is going from minus 2 to 2. So this is, you know, the whole disk of radius 2, which can be described better, right, in terms of polar coordinates, right? This is just 0 less than or equal to r less than or equal to 2, 0 less than or equal to theta less than or equal to 2 pi, right, in polar coordinates. As a polar region. And then, of course, we've got this x squared, you know, minus y squared here. So this transformed into a polar integral is, all right, so sorry, this is y equals 4 minus x squared positive, y equals minus 4 minus x squared negative, and then going from minus 2 to 2. So it's that whole disk there, but just here in terms of r and theta, it's just like that. X is r cosine theta, times 4 minus x squared plus y squared is r squared. So it's minus, right, x squared plus y squared, like that. So 4 minus r squared, and then the dy dx is r dr d theta. So what we've got here is, well, what we got here, unfortunately, is a travesty, because the integral is what? this integral? So let's do d theta dr. What's the integral? This double integral. What's the integral of cosine theta from 0 to 2 pi? Right, this is all r. That's all constants, right? So let me rewrite it. So this is integral from 0 to 2 pi, and then from 0 to 2 for r. So we got r squared, 4 minus r squared, cosine theta, d theta dr. What is this? That's a constant with regard to theta. Right, r squared times 4 minus r squared, that's a constant with regard to theta. So we're just integrating cosine theta from 0 to 2 pi. You guys, you're like, are you there? What's this integral? Or this theta, I guess. Guys, seriously? What's the integral of cosine from 0 to 2 pi? Look at the area of this thing. What is it?
It'd just be 0.
0. So, I mean, to make the problem more interesting, if I were them, I would have just done the integral over the top half of the circle. So, you know, so this is unfortunate, but, you know, to make the problem more interesting, we could do e equal to, so 0 less than or equal to, minus 2 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 4 minus x squared. That way it's just the top half of the circle. And then 0 less than or equal to z less than or equal to 4 minus x squared minus y squared. So if you did e this way, then it would play out like this. So this is equal to that, is equal to, sorry, there's a 0 here, is equal to this integral, but with a 0 down there. So that first iteration of the iterated integral would play out to be exactly the same, except just having a 0 for the boundary right here. So now the region that's being integrated for this double integral is just the top half. So we just have this, in which case the boundary for r is still 0 to 2, but for theta is from 0 to pi. It's from 0 to pi. So in which case this integral would look like this. So instead of a 2 pi up here, it would just be pi. And the integral from 0 to pi of cosine is 2. All right, so 2. So now I got 4r squared minus r to the 4th dr. So this would become 4/3, well, I'll bring through the 2, 8/3 r to the 3rd minus 2/5 r to the 5th from 0 to 2. So that's 8, so 64 over 3. Right, 8 times 8. This one is 32 times 2, 64 over 5. A third minus a fifth is what? So this is 5 minus 3 is 2 over 15. So 128 over 15. All right, so if you want to make that problem just a little more interesting, then you could just do the integral from 0 to pi.
So what does when we did it the first way around, that it equals 0, does that mean that the object it's just a hollow object, it has no mass?
No, what happened is, so what is this object looking like? Let's draw it. So in the xy plane, the region is that full circle there. And then in when you take it into XYZ space, this surface up here is that upside down paraboloid, which looks like this. Z equals 4 minus x squared plus y squared. Looks like that. Right? Z equals x squared plus y squared. That's that paraboloid, that paraboloid thing that looks like this. Right? So here we're flipping it upside down and putting its apex or its turning point up at z equal to 4. So it's coming down, and then in the xy plane, it intersects the xy plane in this circle of radius 2. Right? If you let z equal to 0, then you get 4 equals x squared plus y squared. That's the circle of radius 2, right? So this is what this thing looks like. It's this parabolic cap kind of thing. Okay, not a sphere, right? I mean, a parabola isn't a circle. And then the density function, so f of x, y, z, is just equal to z, right? So this region is totally like symmetric about the xy plane and the, sorry, not the xy plane, the xz plane and the yz plane. Well, it's symmetric about the yz plane, right? So the yz plane is right here. And this thing is symmetric. And then for every x value you got here, you got the negative x value of it over there, right? So the function, it just kind of cancels out, right? I mean, for every point of so much density here, so like the density right there is what? The density right here is 2, or f of x, y, z is x, excuse me. So the density right here is 2. The density right here is like 1 over root 2. Right? But the density over here is negative 2. And the density over here is negative 1 over root 2. So you have this region of positive density and the region of negative density that are the same. Right? This positive density and that negative density, this positive mass and this negative mass, they cancel each other out. I know it's funny to think of mass in terms of negative numbers, but I mean, it's no weirder than thinking of areas as negative numbers, like you do with ordinary integrals. Okay, so you have positive mass and negative mass, mass in quotes, right? With integrals, you have positive area and negative area, with area in quotes. Is that a good explanation? Does that answer your question?
Yeah, thank you.
Just like the integral, so I mean, with cosine, you don't see it as well as with sine, right? I mean, so here's like y equals sine x from 0 to 2 pi, right? So the integral from 0 to 2 pi of sine x is 0, right? Because you got this positive bit over here. and this negative bit have the same area, except this area is negative. Each hump is got area too. So they just cancel each other out. And the reason why integrals, give rise to this weird notions of negative mass and negative area is because of the definition of an integral. It's a Riemann sum, right? With the triple integral, it's the Riemann sum of f, x, I, y, j, z, k, delta v, right? The function f times delta v, well, the f can be positive or negative. When it's positive, and you think of it as mass per unit volume squared times volume, you get just mass, right? Mass per unit volume times volume is just mass, right? But the function could be negative, in which case you think, okay, fine, it's a negative mass. Now, normally, like when you do actual physics applications of things, quantities that should be positive are positive. But when you're just playing with the math, you can just think of, weird things that would, suit the situation. All right. 202. So in number 202, on my notes say I've got another typo. So calculate the following triple integral. Triple integral z dv. So calculate triple integral of z dv. 2 minus 2y is less than or equal to x is less than or equal to 2 plus square root y. Right here. This is supposed to be a 1, not an x. Not 1x. It's just supposed to be a 1. So that's a typo right there. Okay, so 2 minus 2y. So it should be written the other way around. So 0 to 1 for y, 2 to 3 for z. Two to 3 for z. And 2 minus 2y less than or equal to x less than or equal to 2 plus square root y. Yeah. Okay, so again, the region, so it's triple integral over e, where e is this thing here. The first variable is bounded by constants. So y is bounded by constants. Z is bounded by functions of y. I mean, there's no y's appearing there, but you can just say these are functions of y. They're just constant functions with regard to y. So these can actually be switched. I could do z, y, and then x, or y, z, and then x. Doesn't matter. But the x is bounded by functions of y and z. So, well, actually, I could move this up here. Well, let's just leave it at that. Let's do the z first, I think. Let's do the z. So 2 less than or equal to z less than or equal to 3, 0 less than or equal to y less than or equal to 1. Okay, so z is bounded by constants, y bounded by functions of z, and x bounded by functions of y and z. Of course, it's just y is showing, but that's fine. Functions of at most y and or z. So this is triple integral, triple iterated integral, z from 2 to 3, got to go bottom to top. 2 minus 2y to 2 plus square root y and then 0 to 1 for y, and then 2 to 3 for z, right? Going from bottom to top. Z, dx, dy, dz. Antiderivative with regard to x is just zx from x equals 2 minus 2y to x equals 2 plus square root y. So it's just the difference of these two times z. And then I've got dy dz. So this is equal to integral from 2 to 3, integral from 0 to 1, z times 2 plus root y minus 2 minus 2y. So I got root y plus 2y, dy dz. So integral from 2 to 3, integral from 0 to 1, z times root y plus 2y. So I'm going to put y to the 1/2. dy dz. Antiderivative with regard to y. Again, z is a constant, so it's just hanging out there. So 3/2 to 2/3, y to the 3/2 plus y squared from y equals 0 to y equals 1 dz. So this is going to be 2/3 plus 1. So z times 2/3 plus 1 dz. So that is 5/3. So 5/3, the integral from 2 to 3, z dz. So this is 5 over 6 z squared from z equals 2 to z equals 3. So that's 5/6. 9 minus 4 is 5. So 25 over 6. So let me note the typo there. So that's just supposed to be a 1. Let me note it up here as well in this problem. So there's a typo in the book. Oops, there's supposed to be a negative there. In the book. All right. $210. So in 210, so they're doing the same thing. So we don't need to do this one because let's save 210 until section 5.5. Okay, so we'll talk about section 5.5 and then we'll do 210. Okay. So save this until section 5.5, which hopefully we'll get to in just a few minutes here. This is something that really should be done. So section 5.5 is in terms of, triple integrals in terms of cylindrical and spherical coordinates. And this is something that really should be done in cylindrical coordinates. I don't think it's like a great bang up idea to introduce it before you actually talk about it. So So we'll just wait until that section, and then we'll come back to this problem, because you really can't do it without cylindrical coordinates. Well, you could, it's just not going to be real easy. It's going to be a big pain. All right, so problem 222 is next. 222. So find the average value of the function f x y z equal to x y z. So the average value. So 222. So given f of x y z, over some three-dimensional e, right? The average value of f over e is equal to 1 over the volume of e, triple integral f x y z dv. So just like the single variable function and the double variable function. The single variable function, the average value of f over the interval, is 1 over the length of the interval. So 1 over the measure of the interval, which is length in one dimension, fx dx. For two dimension, the measure of the region is area. So like we talked about in the last section, it's 1 over area, double integral fxy dA. Now, through similar calculations as we did before, it turns into 1 over the measure of E. Since E is a three-dimensional thing, it's a volume. So 1 over the volume, triple integral f dv. So here, so with 222, it is the triple integral over that box of x, y, z, d, dx, dy, dz, in any order. Any guesses what it should be? Oh, I'm sorry. Here it is 1 over the volume of the box. Forgot about that. 1 over the volume of the box, which is just that cube. So this is 1, 1, 1, and then this is 1, 1, 1, 1 over here. So it's the cube whose sides have length 1. And the volume of that guy is just 1. Any guesses as to what that average value is going to be? Well, what's the average value over just, and since the function is x, y, z, what's the average value of the function x from 0 to 1? It's a half. The average value of the function y, of the double variable function xy over the square is going to be a half times a half. It's a quarter. This one's going to be an eighth. Half times a half times a half, I bet. So let's check it out. So first iteration, x, y, z squared from 0 to 1, oops, not z, first comes x. X squared y, z, and this is dy, dz. So from 0 to 1, you just get a half. Pull that out front. Yz, dy, dz. And then you do this a couple more times. So 1/2 antiderivative is 1/2 y squared z. From 0 to 1, dz. So that becomes 1/4. Integral from 0 to 1, z dz, and you get 1/8. So average value of the function x, y, z over that box whose sides are 0, 1, 0, 1, 0 to 1, 0 to 1, 0 to 1. The average value is an eighth. Because the average value of each variable is a half. So it's a half times a half times a half. That's not a proof, that's just intuition. The actual calculation tells you it's this. 222, 224. Find the volume of the solid that lies under the plane 2x plus y plus z equals 8, and whose projection onto the xy plane is bounded by x equals sine inverse y, y equals 0, and x equals a half. So, so we've got this plane. So where's the plane? The plane, so I'm not going to draw it exactly. Here's this plane. I don't care what it looks like exactly. And the plane is, where is it? 2x plus y plus z equals 8. So 2x plus y plus z equals 8. And then you're talking about the volume under the plane and above some region in the xy plane. So it's something like that. Okay, without getting too, crazy about the explanation. It just looks like that. All right, and the projection down here in the xy plane is as follows. So the projection into the xy plane bounded by, and they have this nasty arc sine thing going on here. So x is sine inverse of y. So that's just y equals sine x, of course. Y equals sine x, y equals 0, and x equals square root 2. Or x equals square root 2? X equals pi over 2, sorry. Right, so it looks like this in the xy plane. Y equals sine x, y equals 0, and x equals pi over 2. So it's just that. Right, so let's describe the region. Right, so first let's go with the x. So x goes from 0 to pi over 2. Right, x goes from 0 to pi over 2. And then y goes from where to where? Where does y go from in terms of x? Right, 0 from here to here. From 0 to sine x. And then given the xy point in this region here, which is this region there, the z goes from 0, I should use a different color here. So this is x, y, 0. The z goes from here to here. From 0 in the xy plane to this thing here, which is z is equal to 8 minus 2x minus y. Right, so I have x bounded with a constant, x bounded with a constant, y bounded by function of x, z bounded by functions of x and y. So classic setup. What do they want us to do? I'm sorry, 224. Oh, find the volume. So find the volume of that solid. So I mean, in terms of triple integrals, the volume of E is the triple integral over E of 1 dV. Or you can think of it as the double integral of this function here, 8 minus 2x minus y over this region for x and y. When you iterate the integral, it just gives you the same thing. But conceptually, it's nice to know this, right? That the volume is just 1. So the thing of constant density, 1, has mass 1 times the, 1, which is the density per unit volume, times volume, right? So if you have density 1 throughout, then the total mass is just 1 times the volume, which is just volume. So it's the triple integral, triple iterated integral, 0 to 8 minus 2x minus y, 0 to sine x, and then 0 to pi over 2, 1, and then this is dz, dy, dx, bottom to top. So we got the double integral from 0 to sine x, and then 0 to pi over 2. So the antiderivative 1 is z, so you just get that right there. So 8 minus 2x minus y minus 0. We don't have to worry about that. dy dx, right? So it's just a double integral of the boundaries on z. So double integral of the boundaries on z, the difference of the boundaries on z. Now, if one of the boundaries for z isn't 0, then you have to think of it as a triple integral more so than a double integral. Right? Unless you want to do the top surface minus the bottom surface. I mean, there's different ways to think about it. So antiderivative is 8 pi over 2, 8y minus 2xy minus 1/2 y squared from 0 to sine x dx. So this becomes integral from 0 to pi over 2. So this is y equals 0 to y equals sine x. So it's 8 minus 2x times sine x minus 1/2 sine squared x dx. So a little bit of a nasty integral here. So we're going to have to separate these. So integral from 0 to pi over 2, 8 minus 2x sine x minus 1/2 integral from, or dx, minus 1/2 integral from 0 to pi over 2 sine squared x dx. This one, we're going to use parts. U equals the polynomial, dv is the trig function, so du is minus 2, and v is minus cosine. So this first integral is u times v, so it's 2x minus 8 cosine x from 0 to pi, and then minus v du, so it's minus 2, not pi, but pi over 2, cosine x, minus, this one you got to use that double angle formula, 1/4, 1 minus cosine 2x dx. So at pi over 2 here, so this is pi minus 8, well, that's going to be 0, because cosine of pi over 2 is 0. Minus, at 0, this is minus 8 times 1. I mean, minus 8 times 1, so minus 8. 2 sine x from 0 to pi over 2. Minus 1/4 x minus 1/2 sine x from sine 2x from 0 to pi over 2. So this is 8. And at pi over 2, this is 1. So minus 2. And at 0, it's 0. Minus 1/4. So this one becomes just pi over 2. And this one is 0 in both spots. So we have 6 minus pi over 8. I believe that's right. Let's see. No. Okay. So what number was that? That was 224. I believe that's the last one in this section. Yeah, 224. Okay. So now to 242. To section 5.5. So we'll get a jump on that. So let's go back to number 210 from the previous section. So number 210 from the previous section in the text is talking about a region that's really should be described in terms of cylindrical coordinates. So here we've got x squared plus y squared less than or equal to 4, y bigger than 1, x bigger than 0. So let's write the whole region. So in number 210, so the region described is 0 less than or equal to z less than or equal to 4x squared plus y squared. Okay, and then x and y, you got x squared plus y squared less than or equal to 4. So that's within the circle of radius 2. Y bigger than 1, x bigger than 0. Right, so the boundary for z is good enough, but let's talk about the boundary for x and y. So x squared plus y squared is less than or equal to 4. So that's within the circle of radius 2. Why is it always so hard to draw a circle? And then here is the line y equals 1 right here. And here is the line x equals 0. That's just the y-axis. So we're talking about this. All right, so they're talking about this region right here. Well, what is the angle there? Oh, see, that is just awful what I did. Better, okay. Still horrendous, but better. What is the angle here? Right, where this is the point. Actually, maybe it's not quite so bad. This is the point y equals 1. All right, so if y equals 1, so y equals 1, and then x squared plus y squared is equal to 2. So x is equal to root 3. So that's the point 1 root 3. Or sorry, root 3 and then 1. Right, which is twice I guess what I drew at first was not so bad. No, it was so bad. Still bad. All right, so the x, so I mean, if you look at this on the circle of radius 1, if you factor out a 2, this is the point cosine sine, where cosine is root 3 over 2, sine is 1/2. So this is theta equal to pi over 6. Right, so this region here, okay, so we've got the line y equals 1. So this is r sine theta equals 1. So r is 1 over sine theta, or cosecant theta. All right, so this is r equals cosecant theta. This line y is equal to 1. And then this is r equal to 2. So the region being described is as follows. So we have, pi over 6 is less than or equal to theta is less than or equal to pi over 2. And then cosecant theta is less than or equal to y is less than or equal to, less than or equal to r, is less than or equal to r is less than or equal to 2, right? So we're going from cosecant. So if you got some theta in this region, the r is going from here to here, which is the cosecant to 2. So cosecant is less than r is less than 2. And then z is just going from 0 to 4x squared plus y squared. Which you can just call 4r squared if you feel like it. Right, same as 4r squared, if you prefer. So this is the region being described, which is, described in terms of cylindrical coordinates. Right? The region in the xy plane is given by theta and r in polar coordinates, and the z is just given in terms of r and theta. Right? The bounds for x and y are given in terms of r and theta, so that's in polar coordinates in the xy plane. And then the z is given by bounds in terms of r and theta, or in terms of x and y, because you're going to convert them to r and theta later. So you can convert them at the beginning or convert them at the end, doesn't matter. So it's 0 is less than z is less than 4 plus x squared, right? So here in the book, we know z goes from 0 to 4x squared plus y squared. And then the x squared, the x and y have these boundaries, and that took a little bit of finesse to figure out, how to describe that region in terms of polar coordinates. But now we're trying to calculate the triple integral over e, call it e, of y dv. Triple integral over e of y dv. So this is, in terms of cylindrical coordinates, 0 to 4 r squared, or 4x squared plus y squared. It doesn't matter, because when you calculate it, you're still going to have to, convert it to the x and y to polar coordinates. So you can do it right at the beginning, or do it when you need to. And then the r goes from cosecant theta to 2. And the theta goes from pi over 6 to pi over 2. Y is r cosine theta, r sine theta. And then the dv becomes dz r dr d theta. All right, so with the cylindrical coordinates, z is just z. And then the x and y, the dx and the dy become r dr d theta. So antiderivative. So well, let's clean this up here. Bring the r over here. So it's pi over 6 to pi over 2. Cosecant theta to 2 r squared sine of theta dz dr d theta. So there's no z's here, so it's just a z. Oops, I lost my integral. 0 to 4r squared. R squared. Oh my goodness. R squared sine of theta dz dr d theta. So there's no z's here, right? It's just a constant with regard to z. So the integral with respect to z is just the constant times the difference here, which is just 4r squared. So this becomes 4r to the 4th sine theta. So cosecant theta to 2 pi over 6 to pi over 2, 4r to the 4th sine of theta dr d theta. So what do we have here? Antiderivative with regard to r. So the sine theta is just a constant. So the antiderivative with regard to r, page here, is 4/5 r to the 5th from r equals cosecant theta to r equals 2 d theta. So what we've got is, so 32 times 4, so 128. So 128 over 5 sine theta minus cosecant to the 5th theta sine of theta d theta. So cosecant to the 5th times sine, the sine gets rid of one of the cosecants for you. So this becomes 128 over 5 sine of theta minus 4/5 cosecant to the 4th theta d theta. I am not going to bust out the integration by parts and all that junk for this. The worst integrals in town. Cosecant to the 4th. No, actually, it's not that bad. Let's not waste time on that. Where's my Wolfram alpha? So antiderivative cosecant to the, where'd you go? Cosecant to the 4th x. So minus 1/3 cotangent x. And squared plus 2. Alright. Well, anyway, this one is minus 128 over 5 cosine theta minus 4/5 4 over 15 cotangent x cotangent theta times cosecant squared theta plus 2. And all this mess from pi over 2 to pi over 6. So, or from pi over 6 to pi over 2. Well, let me clean this up. 128 over 5 cosine theta. I'll multiply that through plus 4 over 15 cotangent theta times cosecant squared theta plus 2 from pi over 6 to pi over 2. All right, so at pi over 2, this is 0. And then at pi over 6, this is root 3 over 2. So plus, so 64 root 3 over 5. So that was at pi over 2 and pi over 6. And we're subtracting a negative, so it becomes a plus. 4 over 15 cotangent is cosine over sine. So cosine, so this is 0. This is 0 here. Right? 0 minus 4 over 15. So at pi over 6, cosine is root 3 over 2 over 1/2, so that's root 3. Cosecant squared at pi over 6. So sine is 1/2, so cosecant is 2. So it's 4 plus 2 is 4. So 64 root 3 over 5 minus 16 root 3 over 15. So that's going to simplify a little bit. Well, I'm not going to do it. Is that what I got last time I did this? Yeah. Actually, I have an 8 there. Just make sure that's right. Yeah, I think I messed up that 2 there. No, this is correct. Right. So that was a nasty problem. I mean, probably I should mark this one as not appropriate to do. So 210, not appropriate, I don't think. All right. So it's 8:45. So next time we will go over the section on triple integrals in cylindrical and spherical coordinates and calculating centers of mass and moment of inertia. And really, we're only going to do like a couple problems in there. Okay, so watch the video for section 5.5 and 5.6 for next time, and then we won't have class on Monday, so that's for Wednesday, and then on Monday there's no class, and then on Wednesday next week we'll start with some review, and then we'll take the exam for the second half of the class. Okay. And that'll leave us plenty of time to go over all of Chapter 6 for the rest of the semester, okay? And to do our 4th exam and then a final. All right, guys, have a good night, and I will see you next time. Email me with questions or concerns.